Alrighty. Looks like we're live. Alright. So, hello everyone. Welcome back to my stream. In the last stream, we checked out. Oh, sorry, I forgot to switch it to the desk hand. Alright. So, hello everyone. In the last stream, we took a look at this balancing robot that I started working on a long time ago, and we started exploring how to get FreeRTOS networking working on it, so that hopefully we can see some of the data coming off of it. As a refresh, this robot is based on a Pico W, and we hooked up this debug probe, although we didn't actually touch the hardware of the robot in the last video. So today, what we're hopefully going to get done is getting some actual data out of the inertial measurement unit on the robot and over the network and onto our development desktop, so that hopefully we can see the data being streamed off the robot before we get into setting it up such that the motors actually work, so that it balances. But in the last, let's see, so let me switch back to my desktop. All right, so just move this camera out of the way. Turn that light off. All right. So, let's see. Actually, need more things out of the way so I can access my keyboard. Just a second. So in the last stream, we figured out how to get our Pico W on the network, and we did that by first setting up FreeRTOS, so that we can have essentially threading support on our Pico W. And the reason that we kind of want threading support is that the Pico W has 2 cores. So regardless of the I guess I should say development ease, or not development ease, other than the logical organization of having multiple tasks being in multiple threads. The fact that we have multiple cores on the Pico W means that if we have multiple threads, we can actually be running more than one thread simultaneously. So not only can it be concurrent, it can be parallel. So it also just makes network programming a lot easier, because you could, well, at least easier, because you can consider, we could start a task per connection, or we could have a network task that's always blocking, but either way. So so we got FreeRTOS set up, and then we also got the Pico W connecting to my Wi-Fi network, and we left off at, we had this loop where I was noticing that we were getting essentially a failure to connect pretty much every time it started up. So I added this retry loop, essentially, where if it fails to connect to the Wi-Fi, it just waits a second and tries again, and usually picks up the Wi-Fi connection in the second loop. The fact that it reliably fails on the first try and then reliably works on the second try is kind of odd. Something we should probably get to the bottom of eventually. Maybe we have to wait more at the beginning. I don't know. But if I recall correctly, I had also tried to get MDNS working, and if you haven't seen it before, MDNS is the same thing as Avai on Linux or Bonjour on Mac OS. It is otherwise known as multicast DNS, and essentially what it lets you do is have devices on the network broadcast their network name, so that you can connect to them without knowing their IP address using you basically using the hostname.local. So if you have a laptop on the network, called, Nate's laptop, you could log into it potentially. You could potentially see it on the network as Nate's laptop.local. And in this case, our hostname is Pico W with some junk padded onto the end of it. And it wasn't working at the end of the last stream. And turns out the reason that it wasn't working was because I copied the wrong IP stack configuration file, and I almost had it, but I didn't quite. This stack size by default was 1024 bytes, or 1 kilobyte. specifically in the samples that used MDNS, this was 2048 bytes. And the moment that I changed it, it started working again. Or it actually started working after logging into it. And just to demonstrate that, I uncommented this. So essentially, the main task here starts up the Wi-Fi chip, generates a host name, connects to the Wi-Fi network, and then starts up this MDNS responder, which you previously commented out. And then our loop is just print the host name and then just sit in a busy loop, or sit in a busy loop forever. Basically sleep. What is it? 1 second, just forever in a loop. And that's all it will do. But if we actually build this, compile it, and then we're going to, before we put it on the robot, we're going to put it on a little Pico W I have here. And if we just run that on the Pico W, when it's done flashing, if we switch to the Pico W, we can see that it starts trying to join the Wi-Fi network. It's probably going to fail the first time. Yep. Oh, there we go. Or actually, no, IP is not a failure to connect, but link up. We're 10.0.0.236, but our host name is Pico W 40ee.local. So if we go to if we copy this, we go to a terminal. Or sorry, we say ping 40ee. It'll take it a second, but it should find 10.0.0.236, and it does. So we can actually, doing this, we don't actually have to worry about remembering what the IP addresses or figuring out the IP addresses. And just to not worry about that 40ee thing anymore, because that's kind of annoying. This is just something I copied out of one of the samples. But just to not have to worry about that, what we'll do is, how about we just override that. We will set the host name to, or set host name and copy that host name. What does this function actually do? Define host name name. So what if we just sprintf, let's give ourselves, 32 bytes, and we'll do an sprintf. Actually, that's silly. Char pointer host name. Actually, what am I doing? Wow, I'm really just, we don't have to worry about that. What if we do netif set host name, and then in here we just do Pico balancer, rather than having to worry about the Pico W thing. And just to sate all this stuff, sorry, const char host name equals Pico balancer. We'll just do that. Oops. That is fine. We could probably override that CY43 get MAC address, but we'll just do this for now, just to make the minimal number of changes to our code. So if we compile that and then run that, monitoring ACM0. You should see it come up. And link fail, joining Pico balancer.local. Still the same, because we have the same MAC address, the same IP. Now let's try pinging Pico balancer.local. Hey, and it comes up. Awesome. Perfect. Now we've changed our host name. Perfect. So stop monitoring. All right. So now that we have this simple loop, the first thing that I want to try is actually sending data to my desktop. So the first thing that we're going to do here is we're going to just connect to a UDP socket and we're just going to broadcast off into the void, essentially. So we're going to assume that my desktop is working correctly and that there is somebody listening to us on the correct IP and port. So we're going to first, all right, so let's see. So we're going to first start by setting up a socket address. So, or let's see, set up UDP socket. So presumably if I recall correctly, that should be a struct. Okay, so before we get in here, one last thing. So the other thing that I forgot from the last stream. So I was trying to figure out what the sys and no sys option was. Turns out this this is an LWIP variable, but no sys means that or sys and no sys. No sys means that there is no POSIX-like networking API. So if you remember creating sockets by you make a call to socket, you make a call to connect, you make a call to send receive, with some file descriptor handle ID kind of thing. That is the POSIX networking API. Sys, if LWIP has the sys variable defined, those are available. If LWIP does not have those, or if LWIP does not have sys defined, or if no sys is defined, it is entirely a callback-based implementation. So essentially we can assume that our sys or our system here is FreeRTOS, and because we have the ability to have threads, we can use a declared or an imperative declarative blocking networking model or network socket model, because since we have threads, we're not blocking the CPU forever just waiting on a receive. So if there is no system, no FreeRTOS, or you're just running this without FreeRTOS because some design decision. No sys means there's no POSIX-like API. Sys means that there is. So we will never be looking at no sys again, really, because the POSIX API is kind of a little more straightforward, I guess, to think about. At least for me. So we're going to go through and assume that our POSIX stuff is available. So if we want to connect to my desktop, which is IP address 10.0.0.10 on my local network, and the listeners. Either way, so that should be a struct sock adder in, and we're going to call that address, and then address family should be AF inet. And then address syn port should equal htons. We're just going to say we're going to use port 3000. And then we're going to use a command called I think it's IP adder pton or aton. I think it's aton on LWIP. So the address is going to be, let's see here, it's going to be 10.0.0.10, and this is going to be address.syn adder. If we go to that definition here. Right, int. So it'll return if it could be converted, 0 on failure. All right, so go back to Pico balancer here. We're going to say if equal 0. Let's say printf failed to convert address to network format. We'll just say that. And then v, and then null. Just to exit this. And let's see if this compiles. Oh dear. Incompatible formats, and maybe, oh, it's probably just got to convert this to a pointer. And then compile it again. Nope, that's not it. Incompatible pointer types. Alright, if I recall, okay, IP adder. This is the structure for this. All right, so how do we convert from LWIP's IP address structure to the actual underlying structured format? Wait, do we really not have a low AP socket? So if we go to the ping sample, we should have, we don't have LWIP socket. No, we're all right, hold on. Socket is 1. Okay. So we've defined our socket. Okay, so this is just being silly. That is available. All right. Let's see if we're just missing. No, we've got that. What are we missing? On top, family address. Maybe there's a reverse of this. INET adder. Maybe there's an INET IPv4 address to adder. Maybe there's a that. All right, let's try INET. Adder from IP. Okay, maybe. Target adder. We're gonna say address.syn adder. And the source IP address is going to be IP adder. Maybe that's a thing. Is that a thing? Does that work? Maybe that works. Nope. Invalid type marking. Oh, wait. I'm sorry. Lol, I messed up. Derp. Hey, now we finished. Cool. We built. That's good. Okay, set up UDP socket. So set up a sock adder structure for IP 10.0.0.10 port 3000. All right. So now presumably you can set up a socket. So set up a socket. Say auto, or well, let's see. So let's see, socket. I don't know what this actually returns. So we're going to assume this is an int. Int socket int sock equals socket Domain is probably inet. Type is probably sock dgram. Protocol, I'm assuming, is IP. Proto UDP. Alright. Let's see if that fails. So what does that return? LWIP socket. Oh dear. Alright, and returns an integer. Cool. Alright. Oh. Let's see what the return types of LWIP socket are. SD style socket API. We're just trying to see if the return types are the same or different from standard Unix. So we'll just we'll assume that 0 means failure. I mean -1. -1 means failure. Less than 0 means failure. Yeah, that's the same. Cool. Say if sock equals -1, failed to create a UDP socket. This vtask delete function again is means it'll kill the thread. Alright, set up UDP socket. Create a socket handle. And then we're going to call connect on this socket. And if you call connect on a UDP socket, it just binds the standard send to. So we're going to call connect on sock. We're going to say address and size of address. Int res equals if res -1 printf failed to connect to UDP socket. All right. All right. So that should, in theory, be enough to connect to a UDP socket. So I think error, yeah, if error's -1. Okay. Actually, we'll be friendly. Close sock. All right. So now that we've got this, let's try compiling this, and it's not building sock header in. Okay, maybe we just pass address. No. Right, it's construct. Oh, spelled that. All right, cool. Now let's run that on our Pico W. All right. Monitor. All right. Okay, cool. Joining. Perfect. It did actually connect to UDP. Or, well, I should say it. The socket's valid. Alright, so we'll stop monitoring. Let's ping this to make sure that we're still up. Perfect, we're still up. Alright, so now let's start sending ourselves some data. Alright, so in theory, all we need to do is send some chunk. Data to send, data to send. We're going to say char message 64 0 fprintf. Actually, sorry. S and printf. Message size of message. Okay, we're going to say message from Pico balancer equals %d. We'll say num plus plus, and then remember to go create a thing. See it when. All right. And then we're going to say send. I'm going to say res equals send sock message len. Say 0 for the flags. I'm not sure what that is. If res less than 0, def send encountered, and error equals to %d. Okay. Let's compile that, see if it works. All right, cool. We have got a socket we're going to send just a message out on over the network to hopefully my computer, which will hopefully be listening. But let's try to run this and see if it runs on the Pico W. We'll start monitoring, switch to the Raspberry Pi, Pico. All right. See what happens. Joining, no IP, link up. All right. And presumably it's sending. We will see, we will see. So, now that we've got a Pico W sending on our network, we need some kind of receiver. And I think this is a perfect example of just a simple Python script that we could write. So we shall create ourselves a tools directory in here. Then we'll just make ourselves a UDP receiver.py. I think that's the correct shebang. All right, so I don't know how to do Python networking. So we're going to just do a quick Google for UDP Python receiver, and use, what is it? Actually, sorry, I want to use async UDP. All right, that's a really simple example. I love that. All right, so what we're going to do here is select an interpreter. We're going to create a virtual environment using VM, using my current Python. Following environment is selected. Just let it create a new terminal for us that's in the correct virtual environment, and That's such a gross addition to the name. Either way, pip install async UDP. Perfect. So should just be able to do import async IO, import async UDP, def main equals await async UDP dot create socket local adder equals, you know what, window wildcard 2000, and then while true, say data adder equals await dot receive from print data adder, and we're not gonna echo that, but then we'll do async io dot run main. All right, now let's see if that works. Tools, right. No results. This is kind of one of those, did we do it right or did we do it wrong? Print just to make sure that we got into our loop here. All right. All right, so actually, you know what? Let's see. Let me make sure this port's open in my firewall. So it might not be. I have 3000 TCP, but not 3000 UDP open. Perfect. Okay, sudo UFW allow 3000 UDP. Perfect. Hey, there we go. And now we are receiving data from the Pico W on my desktop. So that means that, perfect. Cool. So for those who are just joining us, we have a program written in C, or written for the Pico W in C using FreeRTOS, LWIP, and the onboard Wi-Fi on the Pico W. And we have written ourselves a tiny little simple program here that essentially sets up the Wi-Fi, connects to my network, and then just starts broadcasting out data to a specific IP and port, and hopefully something on the other end is listening. And we can use a very simple little UDP, async Python program here that just sits there and listens for any data coming in on that port with a wildcard on my desktop. And as you can see, the message which we send on the Pico W, which we do a snprintf, so blah, blah, we do a create a message from Pico Balancer, just some integer we keep track of, sends out the data once a second, and then we can see on our desktop we receive this, message from Pico Balancer, number equals something, and then it's being sent from 10.0.0236, which if we look at our serial monitor is the address of the Pico W. So this means that we have data, this means that we actually have a network connect. We have a usable network connection from the Pico W to my desktop, meaning that anytime we want to send data, we can. Or we now have a way to wirelessly send data to my desktop. All right, so now that we've demonstrated that we have UDP receiving working, let's see if we can spin up this tool script in Jupyter Notebooks. Let's see what happens if we try to run async in Jupyter Notebooks. I'm going to do pip install Jupyter to get Jupyter Notebooks. Jupyter Notebooks being an interactive Python environment. It's really common in the scientific world, or in the research world, or either way. So if we want to do that, we'll go to Tools. We'll do Jupyter. Just run Jupyter Notebook. That'll pop up something in our web browser here. Actually, honestly, this is just... All right, we're going to create a new notebook. We're going to use Python 3. Select. And then we're going to say, convert this to Markdown. We're going to do Pico W balancer, data tools, or whatever. All right. And we're going to try copying that little Python program into here to see what happens. And then we should be able to do this. Oh, right. That's right. That's how this works. Okay. Because it's running from a running event loop, we can do we can just do create task. Hey, there we go. Okay. Perfect. Now we can oh dear, I'll just hit stop. Oh. Right. This is why Jupyter. Okay. I wonder if there's a better way of doing this. Ooh, that's funny. Right. How do we stop the Python async IO task? Maybe it's cancel. Terminate. There we go. Oh. Cancel. Let's actually restart the kernel here. There we go. Okay, that's how we do that. Oh, that's not running. Okay. Maybe Jupyter Notebooks isn't the best tool for this, but later on we're going to want to use something for the visualizations. So we're going to have to do a better job of making this cancelable. So either way, I'll just restart that again. But yeah, fine. Yes, we do have a way of getting data now, even if it's a bit kludgy. Oh, I cancel the task. Perfect. And restart that. Okay, so back to the Pico balancer. Alrighty, so now what to do? All right, so we're currently using Pico W on the desk to do this rather than the one on the robot. So now let's just make sure that we can flash and upload this to the robot using the debug adapter. All right, so let me just make sure that these batteries are okay. So let me do this, grab a multimeter, and I just need two that are roughly the same voltage level here, because I did not think about, so it's 4.10 volts. All right, we got two that are roughly equal. And these are the 18650 cells, or I should say 18650 cells. All right, welcome new people. All right, so we are just inserting the 18650s into the robot here, at least into the logic side of the robot. We haven't powered this up in a long time. All right, everything's still looks to be hooked up correctly, so hopefully we won't get the magic smoke or worse lithium fires. Ah, yes, powered up. Cool. I see red lights and not fire. All right, so we are going to switch over to hopefully using the debug adapter. Now we've connected that. All right. So let's see if, okay, well, I mean, this is obviously going to have errored out. And we're not going to be using the serial monitor anymore because we have the debug adapter and we don't have a UART. So we're going to see what happens if we launch using the debugger and not start. GDB session ended. Next session to start. GDB session. Why did that not work? Open launch.json. Pico with external and launch target path. All right, maybe. What does it want me to do? Debug, configure, kit, Pico. I mean, launch target path. I mean, that's what we want, right? It's one of these other ones. What does Raspberry Pi tool say? Flash project using this. Well, okay, it is uploading using the debugger. Yeah, I've accidentally stabbed myself with multimeter probes on multiple occasions, unfortunately. It is not fun. They're very sharp. Yep, found a multi. Alright, so presumably, now that we have flashed using SWD with our debug adapter, we should just be able to ping the... no, I don't want to stop. No. We should just be able to ping the balancer again. Presumably this is presumably that would work. Oh, yes. Nope. Alright. Actually, since I take that back. You know, since we flashed with SWD, I don't know if it automatically will start it. So let's reconnect the power here. And, oh! I'm stupid. That's what I did. Of course it's not going to work. We are waiting for a USB connection at the beginning. And we will never get the USB connection because there's no USB plugged into it. So let's comment that out and rerun that. And then we'll flash the project using the debugger. And program start, verified, blah, blah, blah. All right. So give it 10 seconds to initialize here, you know, sleep 10. All right. And there we go. Awesome. We got a new, because this is a different Pico W, we have a new IP address, because that means that we'll have a different MAC address because we have a different, physically different unit. But the MDNS hostname is the same, because the other one's powered down, this one's powered up, and it's hard-coded hostname. So, perfect. And also now, now that we're actually sending out data once a second, and the Wi-Fi's staying staying powered up fully, our ping times went down from several hundred milliseconds to just a handful of milliseconds. So that's fun. All right. So we will rerun our just to verify. Let me just pull this back over so you can see what's going on. Turn the light back on. And switch back to the desk cam. All right. So this is what we're doing right now. We've got the debug adapter plugged. We've got the debug adapter plugged in. We've got two 18650s in, so it's powered up. The Pico W is just buried in there, and so no USB. I mean, there's the debugger obviously, but other than the debugger, there's no connection to the Pico. And if we put it back over here, and move this back out of the way again. Push back to that, sorry. And so, let's kill that ping there. And then go back to our Jupyter Notebooks and restart the kernel. Fire this back up, create a new task. And there we go. We've got, still getting data from the balancer, which is good. All right, I'll cancel that. All right, so we have migrated over to the robot. Now, just to test things, let's see if we can actually freaking run the debugger. So, I don't know why this didn't work before. Let's try Pico debug. Yeah, no, that didn't work. Does the program exist in the file system? Spawn GDB multi-arc. I mean, it should. What if we did C++ debugger? Well, it's definitely trying to flash first. Unable to start debugging. My debugger. Okay, this is external. No, not external OpenOCD. All right. Why did this not work? Well, this did not work out of the box, which is fun. All right. Pico SDK. GDB should be in here, right? Wow. Yeah, we're gonna make fun of me. Name. GDB. Okay, well, I mean, GDB's in here. That didn't work. Oh, this is a directory. Oh. Really? So does the Pico SDK not include GDB? That would be silly to sell a debugger and then do all of this work to put a GDB in here. Oh, no, there it is. There it is. Okay. Woo. All right. ARM none GDB. All right. So it has GDB, but it's not launching the debugger. Get a GDB path. Alright, hold on. Just as a sanity check here. Projects, ARM, test, Pico balancer. Right. On my other screen, I'm looking at my kit configuration, but that includes my Wi-Fi password, and I don't want you to see that. So, all right. So, okay. Compilers contains that. Why is it not finding GDB? Come on. Also, while we're sitting here, we should disable the USB port. Just to remember that. All right. Let's choose these two. Looking like a silly person here. All right. Why? Okay. We're looking for GDB. We're looking for GDB in Raspberry Pi Pico SDK. And for some reason, HTTP path is not being defined. And get compiler path. Presumably, it should be in here somewhere. So I'm not sure what is going on. Where is it? Tool chain path. Where's make path? All right, maybe when tasks, file run flash, file run, maybe in launch, no, not launch, sorry, C++ properties. No, that's just the, hold on. No, that's not a thing, sorry. Where are you? You know what? There's probably a right way to do this, but you know, around here we never do things the right way. We just make things work. So Pico SDK, find ARM none ABI GDB. All right. So what we're gonna do? we're just gonna do something silly. We're gonna go to the launch. We're gonna go to debugger, debug stuff, server started, monitor, get target. Alright, what are all the differences between this stuff? Get GDB path. We are gonna do user home. User home slash Pico SDK slash manually specify the path to GDB. And we'll do that over here too. And we'll do that over here too. And let's see if this works. Hopefully it does. That would be really nice. So we're gonna just pretend like maybe it'll be kind to us. We're gonna put a breakpoint on main. We're gonna go to the Pico thing here. We're gonna do Cortex debug. And see if something happens. Nice! Alright, there we go. We got single stepping in the Pico. Perfect. Perfect. And then let's start. Let's... I wonder how much integration this thing has with FreeRTOS. So let's continue. Hit. Alright. Something happened. Well, progress. External reset detected. Trying to re-examine. Oh well. I'll still consider that a victory. We did demonstrate that the debugger will spin up, but what happens if we hit pause? Alright, cool. Continue. It's entirely possible that because the FreeRTOS resets core 1, that if there's a task that gets put on core 1, it's not hitting a breakpoint. But hey, oh, that worked. Okay, maybe it's just I don't know what that means. Yeah, either way, that's working. Yeah, this is probably really not happy with me for pausing. Oh, there's an active Wi-Fi connection. How badly did we break the whole Wi-Fi system? Well, we can still ping it. And we'll restart the kernel over here. Oh wow, I'm in. Oops, sorry. Restart. 1, 2. There we go. Don't cancel it. Okay, cool. Well, it is still sending a state, even though we did hit a hardware break, even though we did pause it while the Wi-Fi was up. It's still running. All right. So, stop that. Cancel. All right, cool. Kill this dangerous terminal window over here. Wow, 16 concurrent viewers. Nice. Welcome, everyone. All right. So, demonstrated the debugger works. Demonstrated that we can get on the internet. Or, well, at least, well, the last video we demonstrated we could actually ping the internet. So, because we can hit my desktop, we can definitely hit the internet. Or I should say, it's a realistic assumption that we can hit the internet. Last video we ran the sample for NTP, and that was hitting a public NTP server out on the internet. But sending UDP data to my desktop over the network, flashing things to the robot, the debugger, running the robot off some batteries. Everything's powered up. So, now that we have that, now that we've demonstrated we can actually get on the network, what we should probably do now is, I think it's time to get the IMU working. And so the IMU that's in here is a MPU6050 attached on one of the Pico's I2C controllers. I'm thinking we should use the digital motion, just to make life simpler for me and anybody watching, we're going to use the digital motion processor on the, oops, sorry, I tapped the microphone. We're going to use the DMP, which I think stands for digital motion processor, on the MPU6050. There's some example code floating around the internet for that. So the most common library typically used to, or I don't know if it's the most, sorry, I should say, I don't know if it's the most common, but definitely one of the ones I have heard about, is a library called I2C devlib. And this has been around for a long time. And what it does, well, not what it does, I should have, okay. Sorry. Catch my train of thought here again. Right. So this is, wow. This is a community, or guy named Jay Roberg. It is a collection of implementations of an I2C interface for various microcontrollers. Pico, the RP2040, the Pico, just one of them. There's Arduino, BeagleBone, ESP32, PIC18, STM32, tons. And so this is typically maintained. So there's inside here. There's a lot of utility libraries for interfacing with some very common components. Now, I believe the Arduino probably has the most device implementations. And let's be honest, most of these are IMUs or compasses, various bits and things. I think there's an LCD, SSD 1308. Yes. STM32 probably. Yeah. Oh, that's actually quite thin. But one thing to note is that the MPU6050 that's in here, it's not a new. It's what's called a 6-axis IMU. It has a gyroscope and an accelerometer. So while it cannot, notably there's no magnetometer because it's only 6 axes. The 9 axis have magnetometers, but notably it can tell its tilt, which is really all we care about here. It can tell its tilt in the pitch and roll, and it can measure its yaw position relative from wherever the system was initialized at. Because it doesn't have a magnetometer, it can't know its absolute heading, but at least relative to power on orientation. Because the accelerometer, you can calculate the gravity vector, so you can know your absolute tilt and roll, but without a magnetometer, you can't compute your absolute yaw. But realistically, we don't care. We just care about relative movements and our absolute tilt, because we are a balancing robot. We need to know our tilt. So 6x is fine. Where was I going with this? Right. So MPU6050, it's been around forever, and it's dirt cheap. You can get them for... What are they going for right now? I remember spending like $10 on a bag of 5 of them or something. I don't know with what tariffs and crap what they're up to now, but yeah, okay, so $15 for a bag of 5. That's fine. So dirt cheap. They're very well supported. They have some reasonably decent features. Performance, not that great. They're much better IMUs, but these are, again, cheap. Cheap is the operating word. So because this I2C devlib does have an implementation for, is the only device they implement for the RP2040/Pico is the MPU6050. Not why I chose it, but if something is very common and cheap, people will have written software for it, more or less. So the only sample that they even implement from the MPU6050 is the DMP, a DMP sample. So having looked through this before, one of the problems that the work that we're going to have to do, we can't just take this verbatim, because this is written assuming that the thread running I2C has full control over the CPU, no RTOS or anything, so it will just sit there in a busy loop waiting for data from the IMU. So we're going to have to modify the I2C device implementation here. Because if you look at essentially the read byte read the read function, it basically just goes in here, I2C write blocking, and then I2C read timeout. It effectively, it's not using any sort of like RTOS logic. It just sits here blocking. Which what we will do to, hold on, is this implementation inside? No. Okay, I think, yeah, this is the Pico's I2C write blocking function. So just to make this a little easier on ourselves, what we're gonna do, we're gonna take this sample, we're just gonna run it, just see that it works. So we're gonna turn off the code that we've written so far, just for a couple minutes, verify that this works, just make sure that our connections and everything are set up correctly. Then what we'll do is we'll go through here and we will try to make the minimal number of changes possible to get the IMU to work on top of it. To get it to work on top of FreeRTOS in at least something of a relatively forgiving way. A proper implementation would be to go through here and change these blocking calls to... I mean, it's fine if they block the thread that's doing the read, but we don't want it to busy wait the CPU while it's waiting on something. So all we're going to do is we're going to try this, see what happens, then we're going to hack this up to get it to run on top of FreeRTOS, and then we will have it send data over the network that we can see from our Python program, and then we'll hopefully be able to get to, before I run out of time tonight, hopefully we'll be able to get to displaying it on a plot using Bokeh and Jupyter Notebooks or something. So let's grab this I2C devlib code and start from there. So we'll go to a terminal, and let me stop my debugging here, and we'll just reset that. All right, so we're going to go to projects arm, and then we're going to go to test, and we're going to git clone I2C devlib. And then we're going to go to, then what we're going to do is we're going to create another one of these Visual Studio Code windows. New window, and then using the Pico extension, we're going to import a project. Let's see, change projects. ARM test devlib 2040, 6050. I think that's where the CMake list is. So I just see RP2040. Well, actually, examples, MPU, DMP. That's where it is. All right, examples, DMP. There we go. All right, we're going to use the debug probe. We are going to show advanced options, enable CMake tools integration. Going to use all the defaults on everything else, and then we'll say import. And we'll say, oh dear, that didn't work. Fun. So, alright, hold on. Is this is not, okay, what? Hold on, sorry. It's going to have changed files. Sorry, let me close this and reopen it because I think I accidentally told it not to process Git, the Git tree. Close folder. Open sample. Git repository is found. Would you like to open the repository? Yes. Alright, cool. So it added that. If exists, Pico VS Code include Pico VS. That's dangerous. All right, import, do the stuff, MPU60. Okay, so why? What it looks like, either way, we're gonna have to hack this because this is not working. And I believe the code is, so MPU, so if we look at the folder structure of this CMake list, like, yes, we have the DMP port here, which is what we want. But if we actually go into I2C develop over 2040, MPU6050, like this is actually where the other code is. Actually, I2C develop, wow, okay, hold on. There's actually 2 directories up, I think. Yes, that's 2 directories up. This is a few up and over. Which means we're probably going to need to... All right, so sorry. And yeah, the includes are going to fail because obviously they're not in the right folders. So we're going to include MPU6050 DMP port, include CMake current. Wow, all right, I can't type. CMake current list or ///. Because again, we're trying to, so let me just point this terminal at actual directory we're in. So our CMake is running from here. So if we look 2 directories up, that's where our header files that we want to use are, at least for motion apps and the 3D math. So that's 2 up. Wow, right, I forgot my private statement there. And then we're going to need to do CMake current lister //////////// dev itself. And you know what? I didn't read the README, so let's see if they actually made a comment about this. That would have been a good thing to probably check. I do things without reading sometimes. All right, examples. If you vector build, if you build it, go to this example you want to build. CMake .. Oh, to build the one above. Oh, all right. If we followed these examples, it would not have worked. All right. Yeah. All right. I'm not going insane. Okay. Cool. So presumably, so we fixed our CMake, maybe. Hey, we did fix our CMake. So we'll go to, all right, hey, look at that, we did port. Now we need to make sure that we've got the right, okay, sorry. Tripping over my own words here. Okay. All right, we fixed that. We're gonna do CMake tools. Okay, wow. Totally lost my train of thought. I'm sorry. Right. So we were able to we fixed the CMake list, which meant that we were able to compile and build the MPU6050 example. We now need to make sure that we change any sort of assumed I2C pins to the one I actually plugged the IMU into. All right, so let me, all right, I'm gonna be looking down at this, and let me just power it down here. Let me see just exactly which pins I plugged this into. All right, so let me bring up a Pi Pico pinout diagram. If anybody does feel lost, I don't mind answering any questions that you post in chat. I may not see them immediately, but I will try to answer anything. Realistically, I'm just No, that's not what I'm after. I'm sorry. Okay. Pi Pico W. Pin out. Wow. Okay, hold on. Raspberry Pi datasheets. Here we go. Here we go. There we go. That's the image I was looking for. All right. So by default, it's looking for. It's defining in. Oh, so this is a default configuration. Raspberry Pi, because this is in one of the SAMP, the SDK headers. Okay, so default I2C SDA pin is GPIO 4, which is I2C unit 0, and that pin mux. All right, so if anybody's not familiar with the way the Pi Pico actually doesn't have a ton of peripherals in it. It has, well, it's reasonably healthy, but it's got two UARTs. It's got two UARTs, which are your serial interfaces. It's got two asynchronous serial interfaces. Let me be pedantic. It's got two I2C controllers, which is one form of addressable serial bus. It's got two controllers for that, and then it also has two SPI controllers, which is another serial bus. Not an addressable one though. It has chip slot pins that indicate which device it's receiving. But either way, you have two UARTs, you have two I2C controllers, two SPI controllers, you have an analog digital converter, and USB. And as far as hard peripherals go, that's it. Although I should say the important feature is what's called the PIO, the programmable input-output, which is a little bit of a loaded name because many systems have used the term PIO to indicate non-hardware mode of something, like, which I guess also here kind of works too. But either way, if you have a protocol or an interface of some kind that there is not a hardware block for in the Pi Pico, which is quite possible, so you're trying to do CAN or VGA or something, as a quad SPI or something, you can write little programs to run in the PIO blocks to try to implement those peripherals, or at least to accelerate certain parts of those peripherals. We will be using them eventually to count the ticks on the encoders that are on the motors on this robot. But we'll be doing that later. So either way, let me get back on end my digression here. So those peripherals can be mapped to a collection of different input-output pins on the Pico. So that's why you see I2C0 pop up here and over here and over here. Basically, it's what's called the pin mux. You can configure which pins you want the output to be on. You want that peripheral to be available on, which is really nice compared to something like, say, the Arduino, or, okay, the Atmel AVR, the chip that's in the Arduino. Or I guess now it's the microchip AVR, but oh well. Which has very limited set of pin mux options. There are very few configurations. Yeah, most peripherals have dedicated output pins. If maybe two if you're lucky, but realistically, you usually only get one configuration of pins. But on the Pi Pico, most of these peripherals can be stuck on a large collection of pins, which is actually really neat. But I digress. So the default, the SDK default of I2C is I2C0 placed on GPIO 4 and 5. So this I2C0 SDA-SCL pair right here. But it appears that on my Pico W, I have attached, because I like to make sure that everything I do is completely incompatible with everything else, because I'm an idiot. I have attached the IMU to pins. Where's the green one go? Hold on. I'm sorry. I'm using GPIO peers 10 and 11 for my I2C. So I'm using I2C1 on pin 10 and 11. All right. So go back to our DMP thing here, and we're just going to add a definition for, oh dear, define SDA pin as 10. We're going to define SCL pin as 11. And I believe I put the interrupt pin, the purple one, on... you can't tell the colors of my wires. You're not looking at this. Sorry. But just trust me. It's next to the ground. So pin 9. Pin 9 is my interrupt. So define int pin as 9. All right. And define I2C num as unit 1. All right. So we'll go here and we will change. Whoa. I just switched. Sorry, wow, I just lost my place. Right, I change all occurrences to SDA pin. Change all occurrences to SCL pin. Perfect. And now that still won't quite do us, because... Oh, we're gonna have to power this off USB. So it's a good thing that I disconnected the battery. Okay. 24 concurrent viewers. Thank you. Thank you for watching. Okay. All right. So sorry, lost myself again. I do that. Right. I squared C unit 1. So for I squared C init. We need to change I squared C default. So what we'll do here, that is probably pointed at unit 0. Default I squared C instance, which concat, if not defined, instance, what the fuck? Wow, okay, hold on, I'm sorry. We're just going to change this to I squared C 1. I squared C 1. And then we need to make sure that we change, if needed. It's not actually passing that anywhere. So MPU initialize, we'll go here, gyro range, MPU dev adder, MPU something something, I2C dev. It uses a static interface. So we will open file, dev.cpp. What does it do? It does I2C default. So I2C default, we're going to change all instances of I squared C default to I2C 1. Perfect. And hopefully this still compiles. Well, nope, no it does not. Oh, almost does. I2C num. Included from... I see. Okay, sorry. There's an SDK function called I2C num that tells you which I2C unit you're using. So we're not actually using that, so we'll just remove that. All right, compile. And it built. Perfect. All right. So we should now be able to go here, and for our build builds everything. For launch, we're going to use the DMP port. And let me move my connection here. So in the last video, you got to be careful. The battery, the voltage regulator on here for the logic, I have it connected directly to the VBus input on the Pi Pico. So if it's powered up and you plug a USB cable into it, it will send power into your desktop or laptop, which is probably a bad thing. I have disconnected the switching regulator that feeds the Pi Pico, so I can actually connect it to USB without fear of explosions. All right, it is powered up. And then we are going to click run. And that didn't do anything. Because we turned off the USB in the default image. And okay. Apologies. All right, I need to power this up in boot select mode. I'll wait for a little... Yep, there we go. It's in boot select mode. Yeah, so just to elaborate on what we just saw there a little bit. So I plugged in the USB cable into the Pico W that's in the robot. And there is if you are using the USB, the default USB for standard input-output configuration for the Pico, and you don't do your own custom USB configuration, if you just use the one out of the box, there's a tool that comes with the SDK called Pico Tool that will actually let you revert, which will let you flash it like you'd think of with an Arduino. Basically, you can plug the cable into it, and you can just hit upload program, and it'll reboot the device and upload a new program to it. So buried into the default USB implementation, so if you link against the default standard IO USB implementation in the Pico SDK, it implements this bootloader, well, not so much bootloader, but inside of your program, there will actually be the hook to cause it to flash new or to reboot into that boot select mode. Because we disabled but just before I went to the debugger mode on our sample, I turned off the USB interface on the Pico. So when I came into here and then tried to use Pico Tool to upload, which is the default behavior, it failed because the USB interface is down. So I rebooted into boot select mode, which is a mode of which is basically, if you're used to the Pico, you hold down the button and you plug it in and it forces it into boot up mode. So either way, so we've done that, and now we can click run, and we flash the program to the IMU, and then we refresh this, and we start monitoring. And the reason I'm clicking on not the Raspberry Pi is appears that there's a bug in here where if I try to start with selecting the Raspberry Pi's Pico serial interface, it doesn't work. It stopped scrolling. That's not good. Okay, well, it was printing for a while. Does it only print so many, or does it work forever? Maybe. 5.0 overflow. Nope, it's not supposed to stop. Well, we will reset the Pi Pico and see what happens. Alright, refresh. And if we tilt the robot, we can see that the... Oh, this is in Quaternion mode. These are not intuitive to me out of the box, but we can see a few of the axes changing as I try to tilt the robot. And it froze again. That's scary. I don't know if that's my robot being bad or if that's this program being bad. That's unfortunate. Okay, so what we shall do is what we shall do is grab another USB cable and try to find a place that we can... Oh, I need another adapter. Okay. That's not the right one. I'm dropping things. Oh, this is the right bag. Oh, sorry. Just looking for my micro USB to USB-C adapters. Plug one into the debugger. Alright, so we are going to change the way that this works. Stop monitoring. We are going to we're going to do that same hack that we did. We're going to launch. We're going to do that same hack we did with the GDB because well, first we'll see if loading a new project made GDB work correctly, but I presume that it didn't. It won't have. So we're going to attempt to launch debugging of this program with Cortex Debug. Of course, it's not working. All right, so we'll go to the launch settings. We'll just change all occurrences, paste that in. All right, and now we'll try running the debugger. All right, main, perfect. And then continue. And it should be in busy wait until. Perfect. All right. Serial monitor, refresh. So this should be ACM0 start monitoring. No, it's not. Stop monitoring. Start monitoring. Well, that's not working. Hold up. Come on. Oh, it's probably very angry about the US pausing on USB. So we'll change this to a UART. And then compile. And then run. Oh dear, I goofed. Sorry. GDB. We shall flash project using SWD. Oh, there we go. All right. And then we shall then we shall debug project. Cortex debug. All right, and then continue. All right, continue. Fail, not DMP ready. All right, I'll try that again. Cortex debug. All right, well, that didn't work quite the way I hoped, but all right. So we will actually just try to keep using the USB. All right, so DMP quaternion. We'll go back to our CMake lists. Oh, Hassan, thank you. I appreciate that. All right. We'll go back to our CMake lists. We'll switch this back over to the USB version. File. And actually, before we launch this, we will change this. Does it really not have any definitions for this? All right, so we will use yaw pitch roll because despite my best efforts, I cannot read quaternions with I can't intuit quaternion. Or maybe if I looked at them more, I can't really intuit the quaternion from my head. But we will build this again. We will put the Pico into boot select mode and flash this, and hopefully see that. And then we'll run that. And we'll bring up the serial monitor. Actually, start monitoring the Raspberry Pi. Wow, okay, hold on. All right, yaw, pitch, roll. So perfect. Now we've got, as we can see, we've got tilt and yaw. Okay. Well, it just glitched out on me. Okay. Restart it again. So presumably if we roll it all the way over, we're going to roll it all the way the other way, and we got this, the pitch of the robot. And then we got that way, and then we got that way. I say that way, but you can't really see. We got rolling around the wheels, so, or I should say, the way that it would be falling if it was, falling over. So that's the tilting forward and backward. And that's rolling left and right, which we should never really be experiencing. And then we've got twisting about the axis, and that's the yaw. Perfect. Okay. So that's working. So using that... so the implementation in here at least can output values that we like. And let me, as it's getting dark, let me turn the lights on in here. Let me just... All right, there we go. Cool. Lights on, window closed, so it's not so cold. All right, so now we need to actually get porting. Now we need to port this to our FreeRTOS sample. So that's gonna be fun. All right, well, we'll keep this up, and then all right, so close the sample, tasks, launch, EP receivers, all those networking things. All right, so where to start? I2C devlib. All right, so we should probably, actually, let's go back to the IMU project. Let's just start poking it. Let's just start thinking about where in here we're going to need to start making modifications. So the big one clearly is going to be this I2C write blocking. There's 4 calls to that. And I2C read timeout US. All right, so let's actually look at the SDK documentation for these function calls. I'm kind of curious about how timeout works, considering. All right, hardware I2C read blocking with timeout. Attempt to read with timeout. No device present. Okay. No stop. Okay. So, I just see write blocking. Let's go look at the implementation of this blocking internal. Oh my. Okay. Oh, this is actually very quick, short. Okay, only 358 lines. This won't be. Admittedly, I don't know how the I2C hardware in the Pico is constructed off the top of my head, but let's see. Read blocking internal, invalid param, blah, 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 blah. Tight loop content. tight loop contents. What we could probably do is ITC get read available while not abort and not read available. Determine a non-blocking write space available. 0 if no space is available in I2C. Is there a write non-blocking? Hold on. Doesn't really look like it. I think the oh Jesus. Hardware I2C. I think the only blocking. Yeah, there does not appear burst blocking. And what we could do is we could copy this I2C implementation into our code. Realistically, there's only the one header and the one source file. So what we could do is copy this in, and we could just, the easiest thing we could do would be to replace this tight loop contents with just like a scheduler yield. So it means our task would be rescheduled every time there's not something to do. But it would offer a way to free up the CPU. Not that we're really doing any other work right now. So, and buffer. Well, okay. So to be fair, this code should maybe work even with the blocking, because we do have 2 cores. So I mean, FreeRTOS. The cool thing about FreeRTOS is that it is preemptive. So if we do block for too long, the scheduler will kick us off the core and go see if there's something else to do before letting us have the time back. So this should work off this. In theory, this should actually work. So let's copy that I2C devlib stuff into our project and see if it works. All right. So we need some stuff. What we will do is, just for now, just because I'm lazy, we will copy. Oh wait, hold on. Theoretically, we should just be able to change. Okay. I think that we should just be able to rename this to CPP and change our CMake lists. Because I2C devlib is written in C++. So hopefully, I think this will work. Yeah. Well, that doesn't mean it'll work. Let's use the debugger. We'll plug these back into the battery. All right, run. Oh, wow, yeah, right. I need to use the Flash project with SWD. Ping balancer dot local. Get a little bit wake up. Hey, there we go. Cool. It's still, even though we changed the name, it's still working. Cool, cool, cool. Alrighty. So let's copy the. Wow. Okay. Yeah. Copy. So what we're gonna do is we're gonna make a folder in here called I2C devlib. And we are going to copy MPU6050.star to balancer I2C devlib. We're going to copy MPU6050 6-axis. Copy helper 3D math to balancer I2C devlib. We're going to copy cdev.star to Pico balancer I2C devlib. Okay, so if we bring up this example, put a docket over here, close this. What we will then do is, wow, brain fart. Right, so we're gonna add this to our CMake list. And that means that I need to fix this. Hold on, yes. These auto-generated CMake lists kind of suck, I'm gonna be honest. I2C dev lib I2C dev.cpp I2C dev lib slash MPU6050.cpp. Going to target, include directories, Pico balancer, serve private, build interface, project source dir slash I2C devlib. Okay, cool. Compile that, and it's probably going to complain that we don't have hardware I2C available, which we don't. So what we're going to do is we're going to go to Pico, we're going to do Pico I2, no, sorry. Hardware, sorry, It's Pico hardware I2C, I think. Probably not. It's probably just hardware I2C. There we go. All right, cool. Built all the stuff. Let's see if on the internet we can find a Pico SDK FreeRTOS I2C. Oh, okay. I2CC. Well, that's Reddit. Works fine. Okay, well, that's a warning. Okay. So here is a, not updated for 3 years, but here's a DMA-based implementation for I2C on the RP2040. Maybe we can use this later. We'll see if wow, I'm brain farting. We'll try what we have, and then we'll try this if needed. See if there are any issues. No, nobody's filed any issues or PRs. No updates in 3 years. Well, we'll put a pin in that. All right. So let's first start by copying over the initialization code. All right. I2C init. Copy all this fun stuff. I probably already have much of this added. Yeah, stdlib is gone. Arch That's gone. All right, cool. Yeah, fine. There we go. Put this up in the Pico stuff. MPU apps. All right. I'll copy this over. Just to see if it can, really just to see if it can build. Really. File. It does build. Good. Okay. All right. MPU interrupt is true. Nice. All right. Okay. So we're going to init the I2C. We'll do that before we start the scheduler. Initialize I2C 1 bus, mainly I2C 1 bus for the MPU6050. All right. Need LED. I don't really care about the LED. That's fine. Okay. Let's see if we can do the DMP initialization in a thread versus having all of these globals. Although we'll have to do something about the interrupt. Although this doesn't actually use the interrupt, it just kind of spams the reads. But either way, we'll see if we can do this main program loop in a task, including the initialization, because that'd be really neat. Let's first try doing it from main task, and then when we have it working in main task, we'll move it to another task. So once we get all of this stuff up, we're going to do the MPU initialization, DMP port. We shall do this. Oh man, so much junk. We now have the auto thing though. Let me replace this with auto. Let's say ret. Nah, we'll leave it as res. We already have it as res. DMP ready, true. Packet size, get expected later. MPU interrupt status. Hi, button. Alright, my cat is screaming at me. Hi there, girl. Alright, int status. How often is this used? And int status, MPU interrupt, or int. There we go. Does it never update the interrupt status? Interesting. Okay. All right, what we will do is if this is if there's an error. If DMP initialize, do printf failed to initialize MPU6050 DMP. All right, cool. Then we don't have to worry about this DMP ready thingy. All right. Then we can delete all that crap. Auto. Cool. Good size for later comparison. And then what we'll do, all right, so comparison, yaw pitch roll. Okay, so theoretically it's up now. So what we'll do is place a we'll just place a breakpoint there, and we'll compile it, and we'll deploy this code, and hopefully we can see something fun on the debugger. So let's go back here, debug project, Vertex debug. Continue. There we go. Connect. MPU. Heyo, it worked. Ow. Darn it. Alright. I thought I told it to be. I thought this was a debug build. Stop running optimizing, please. Yeah, debug. Oh well. Probably not. I agree. It's probably trying to be friendly about removing things I don't use. Alright, well. We'll change our message to set u equals %u. Honestly, O2x is O2, and this is going to be O4, right? Yeah. O4x and O2x. I'm going to do oops, yeah. Compile. Alright, and then we shall debug. Flashing code. Go back to our and restart the kernel here, yes. Nice, there we go. We got some data back from the IMU. Or well, not data, well, very, very simple initialization statuses. So something that isn't zeros. So we got something, we got something from the IMU. So it's not a complete dumpster fire. All right. So we'll just stop that. We'll cancel this task. Restart our tool here. All right. Perfect. We're doing something. We're doing something. All right. So we will say if programming failed, don't do anything. Well, we're going to cancel our task. So what we're going to do now is, because we're doing yaw pitch roll, we're going to be copying this junk. Oh, not quite there yet. Copying this junk. Copy. Let's not do it in one go. All right. So what we shall do is Okay, what's interesting is that we're just always doing this, which is interesting. So and it to 1. So is 1C, so that's right, it was up. So let's power the thing down and then power it back up. Wait for data. Because if ANDed to 1, which it was, okay. Reset FIFO. Oh, wow, I flipped this in my brain. Not packets, it's int status. Int status 5. So the top bit, so this will never be because it never checks int status again. It only checks it here. And let me just be certain about that. Int status defined up here. We check it there. We never read it again. We only just query. Okay, so so this will never be true, probably. But we'll put it there just in case. If check. All right. I see. Wait for the correct data length. It should be very short wait. All right. It's not like it actually reuses FIFO. Okay, it overwrites FIFO count every freaking time. Okay. All right, well, we can do our own thing here. Okay, so in here we shall FIFO count equals MPU.get FIFO count while we're just gonna skip that for now. We're just gonna skip that for now because this can never be checked, or if FIFO count is 1024. Okay, well, okay. Fine. Continue. Otherwise, we shall await FIFO buffer is 64 bytes. All right. This is bad. Don't code like this. We're just get it. Okay, you went to 8. This is just turbo hacks until we make this better. This is very hacky. This is very bad. Don't do this. This is fine for hacking this up right now. While FIFO what? Okay. Else if FIFO count less than packet size. Continue. Okay. FIFO count less than packet size. Okay, there we go. That's a bit better. Read the file. And then X, that never changes. Okay. Okay. Just copy that. Perfect. Q, gravity, YPR. Q, gravity, YPR. Just copy this for now. We'll just paste this here like dumbasses. Q, gravity, YPR. Ah, I see. Okay. I see. And we'll just merge this. Share message. Message, size of a message. Delete num. All right, delete that. And we'll delete the delay too, yeah. Send. We'll keep that. All right. Now pitch roll. All right. Send orientation. All right. Theoretically, that'll build, right? Compile. Perfect. All right. We do run. Button. What are you doing? Nice. Well, we're getting a lot of data from the. Oh dear. Restart. Sorry, it's just too much code, or too much stuff happening. Sorry. Restart the kernel. We're gonna pull up the terminal here where it'll projects arm test. We'll just use the right. Sorry. To use the terminal here. And we shall restart the. Actually, no, we're gonna kill the debugger. We're gonna do that. And once it connects, hopefully we'll start seeing a bunch of messages coming across. Look at that. We have got Oh, he died. Okay, that's sad. There's some very broken message from the IMU. I don't like that. There's clearly something wrong. Disconnect the debugger here. Since it's wireless, we can pick it up and rotate around the axes, huh? And actually see the data changing. And it froze. Okay, well, we're gonna have to fix the IMU freezing, otherwise this thing's gonna fall the heck over. We're gonna try to put that up, try to wiggle that in there, reboot this again. Try to wiggle this in there as best I can. All right. We're running. We can rotate it. We can rotate it, around. And it does that. We can rotate it, and there goes the roll axis. How's that? And the cool thing is, this is wireless, and so we are sending this inertial data over a wireless link to our desktop. And it died again. All right. Well, it was doing that before, so I'm not entirely convinced that the I2C devlib's I2C implementation is done correctly. But okay, so, but I mean, hey, we've got wireless, we've got the IMU, we've got threads. So let's so just to demonstrate the threading a little more, because we only got I'm gonna end this at 9 Pacific, so we got 20 more minutes here. So just to demonstrate some more of the FreeRTOS stuff, what we shall do now is use we will have a IMU thread that reads the IMU data, and it will send it through a buffer to the network thread, which is our main thread. So we're gonna create our second thread, and hopefully it's not going to explode, because right now we're just running one thread, and maybe that Reddit article, that Reddit post that was describing a core lockup, maybe if that is the I2C and that is a FreeRTOS thing, well, the fact that we'll have two threads means we'll be potentially exacerbating that. But there are other threads inside LWIP on FreeRTOS, so theoretically shouldn't we should already have multiple threads. Either way, so what we shall do is, we're already doing that, so we're going to create another task, and it's going to be called the IMU task. 9 params. And this will be what initializes our MPU. And the MPU was only ever initialized. Oh, wow. Okay, MPU, we did the initialization in here. Oh, okay. So what we'll do is we'll move this up here. Put the MPU in here. Exactly, we don't actually have to do that anymore. Failed to initialize the DMP. Pitch roll. All right, so we're going to use what's called a stream buffer. I think that's probably the best. Stream buffer API, I think. Is it message buffer? Stream buffer versus queues. Maybe we just do a queue. XQ. Create. Slides of long. Create a queue capable of containing 10 unsigned long values. A message. Oh, all right. Well, what we'll do is Q containing 10 long values. Okay. Well, what we will do is we will say struct vector or struct vec3. Wow. Is float x, float y, float z. And then what is a right-hand coordinate system? I think right hand is the one they use in physics, right? Right hand rule. Or what is the Z up coordinate system? Hold on. What does the actual IMU do? It says that Z is the vertical. All right, we're going to use device local instead of physics or anything like that. So Z is the yaw axis, and then Z's yaw, Y is tilt, and then X is roll. Okay, well, let's just reverse to what. Either way. So we're going to define our struct as that. We are going to define a Q handle. X create Q, X Q send. I think we can do a, what if we did PD parameters, X create task. I think test code, PC name, stack dep, PD parameter. Cool. So we don't even have to worry about, okay, so void Q. I'm going to say Q handle. All right, we are going to include Q handle T, which I think is a pointer. Yeah, it's a pointer. Q handle T, Q equals handle T, Q. All right, cool. Fine. This is C++ after all. That's probably going to complain at us for other things. Oh, wow. All right. That's already a pointer. That's why it wasn't building. All right. Either way, fine. Perfect. I'll kill that. Initialization. And then what we shall do is cut all of this stuff. Put that into here. While true. And FIFO. Q send. All right, so what we shall do is, in order to, we'll be a little cheeky. I'll do that. We'll do union. Oh, no. Sorry. Struct. Union. Fine, I'm gonna do it backwards. Just to make this a little easier to read. Float. Yeah. Pitch. Roll. Struct. Float. All right, that should do these anonymous structs. Cool. Union vec3. All right, cool. So we're gonna do a. I think we can do vec3 orientation. Euler. Pitch, Euler.roll. Alright, and time, yeah, to convert it to, and then we're queuing the, read the FIFO. Convert to Euler angles. Gravity vector. Alright, and then we shall execute send from only to Q pointer Euler as of tick type. Oh, interesting. All right, cool. Do port Euler 10 divided by execute send. All right, awesome. All right. Let's see, wait until bytes in FIFO are greater than at least one packet. Perfect. All right, so now we're going to come in here and I don't have to write loop forever. That's implied. It's auto true. All right. So, what am I doing now? I am doing. Fine. Let's just clean this up a little bit. All right. Euler. Gravity. Convert to decimal. And send All right. Cool. And so now in here, what we have to do is create a queue. So what we'll do is we'll kick off the MPU initialization over here. Kick off the MPU thread. So we'll do Q handle T, IMU Q. We'll call it Q IMU equals XQ create. We'll just say 10 and then the size of 3. Then we will say X task create. We'll call this the IMU thread. This is going to be void pointer Q IMU. All right. That's a task and a task handle. IMU. All right. Base type. All right, cool. So we've created the task. Well, true. Orientation, vec3, orientation, and then we do xq receive. I think if you write 0 on the receive, there's no timeout. Return immediately if the queue is empty. Oh, never mind. Port max delay. Okay. You receive Q IMU. Rotation, and then port max delay. If Q send, Q receive, if so if it's not PD pass, then we continue. And then we do orientation.yaw, orientation.pitch, orientation.roll. All right, theoretically, and this should allow us to, all right. So in theory, now we'll have the IMU running in another thread, and we'll receive, so we'll start an IMU thread. It'll run the IMU and send to this queue, this port data, or this orientation data, and then in the main task, we will receive from that queue and then send off onto the network. That'll let the two cores run in parallel. Although there's not really a ton of work that they're doing, you know. All right. So we shall plug back in our little debugger. And do that. shall... I want to see the IMU task start, so let's run this. Main task. Uh-oh. Uh-oh. Well, that's not good. Exit. Uh-oh. Something went wrong. Uh-oh. Uh-oh. Something went wrong. Something went terribly wrong. That's not good. While... Uh-oh. It's not good. Okay, well... I think the queue creation is a thing, but we'll let the thing come up on its own. Maybe if we wait for the thing to fully come up, we start it down here. Ah! Nope. My PV checks waiting termination. Support pending. Uh-oh. Uh-oh. That's not good. That's not good at all. Well then. Not good at all. no, I wonder if this is... Should not be multiple handlers for the same event. Yeah. Something is not working. Or why are we, oh, yeah, so this is that multiple, okay. Let's try to set, let's see. See if there's a way to set the thread affinity. That's bleh. There we go. Task core affinity set. Task. I'm going to set the thread affinity. And actually, I remember there being something about that in the samples. Yeah, all right. Yeah. Hypnosis and using core, and we must bind the main task to one core. And only do we do this. CY Arch FreeRTOS is supposed to take care of it. Maybe. Then why is it not working? Maybe. All right, well, you know what? Can't hurt. Let's try running this. Make list. Oh, right. What if we also set oh. Oh, I'm so sorry. If anybody saw this and was waiting for me to figure it out, here we are. Okay. That's funny. Okay, here's what we did wrong. I ran the main thread twice. I didn't call that IMU task. I made it do the main task. That's what happened. Oh, I feel stupid. Okay. Okay. Let's try this now. Compile. Debug. Run. Do I have to start the thread? But core 0 is stuck on tight loop contents. Read bytes, write blocking. In the initialize. All right, that's not good. Well, what if we also set the thread affinity to 1? If we did that, v task affinity set task IMU 1. So curiosity compile. And then run that. See if it actually works. Nope. Stuck on right blocking. Okay. Well, we might not be able to... Huh. Let's be a little cheeky and kick off the MPU initialization after the Wi-Fi initialization. That's probably for the better. What's that? Oh. Power system. All right, cool. Oh, what? That's not happy. Serious error occurred with GDB. That's not good. You can only set so many breakpoints. Okay. All right, let's try that. I don't have any error breakpoints this thing has. So, we'll see if that changes things. Yeah. I can't. That was it? Really? Okay, cool. Okay, well, that's unfortunate. Doing this on a different task has broken it, which is interesting. Okay, well, rip. Oh, no. Now it's working. What the hell? Alright, hold on. No. It's actually working now. Okay, sorry. Let me reboot this again. All right, I think it's actually working and not failing. Okay. Oh, yeah, it's working. What am I smoking? Okay, cool. And we'll just unplug that. Put that in there. So yes, wireless. Oh, well, it died. Let's figure out what's causing that. We don't know if that's a software bug or a hardware bug or what have you. Probably hardware, probably software. But next time we will check out that DMA_C interface. See if we can get this working again. Did not come back up. I don't know how long it's going to take it to come back up. Connect that. Let's see if it comes back up again. Tools, CDP. There we go. All right. Yeah, we got roll pit. Died again. Okay. Interesting. Well, that's a very interesting thing. All right. What if I just don't touch it? How long will it run? Oh, I'm just sitting on the bench. And it'll let us. And it died. How many of these did it put out? Not many. Oh, there's this bad one. You know, I kind of wonder whether this is just absolutely freaking slamming the what do you call it? Oh, DMP. Or slamming the IMU, because it goes through here. There is an interrupt line coming off of this thing, and it is in fact, rather than checking, it's just repeatedly smashing the FIFO, the check FIFO call. So I wonder if that's the issue. But let's see. But I wonder. All right, but let's see. Under the FIFO. All right, so today we have gotten to, let's see, we have, okay, so yeah, we made, all right, so I think that's where we'll end for today. So we have made a lot of progress. We have taken our simple connect to Wi-Fi, be able to be pingable program, and we added the ability to send data over the network. We added the ability to read from the IMU, to send the IMU data over the network. I guess we didn't get to displaying it necessarily, but next time I guess what we will do is, we will write a bokeh visualizer, and rather than just sitting here saying nothing, presumably this tool will display a plot. Hopefully that won't take us too long next time. I just don't know how to do it off the top of my head, so it's going to represent me figuring something out. So thank you all for watching, and I will send out another notification when I am going to be streaming again. And if you haven't, check out my Bare Metal 386 series, which is about trying to essentially recover an old 386 board from deleting its own BIOS. I haven't posted a video on that in like months, but still working on it. I'm trying to write this emulator for it, and it's taking a lot longer than I thought. But hopefully we'll get another video out on that. So hopefully we'll either, say I'm busy this week. Hopefully maybe next Tuesday. I'm not going to promise that. Hopefully next week we can do another stream on continuing with this Balancer robot. So hope to see you all then, and thank you for watching.